In previous lecture, we already obtained this hyperfine Hamiltonian can be write down a over h bar square and s dot I, that is interaction between the electronic spin and the magnetic spin. Then also it is 1s ground state. One is ground state case, but it is not to resolve the eigenvalue problem, and we should diagonalize this hyperfine perturbation. So in this at this time I will talk about the diagonalization of the hyperfine perturbation. Then if the spin and the isospin are antiparallel with each other, then also the 1s ground state wave function can be write down as the psi 1s rs theta phi is that spatial wave function, and the spin wave function, spin part, and the spin of electron is spin up, and the proton spin down, for example. Then here we should think that the matrix element of the s dot I. So, and we should think that the basis of the SG and plus minus E electronic spin state can have the eigenvalue plus minus h bar over half h bar and plus minus electron, and like that. And the Ig plus minus proton is that the plus minus 1/2 h bar and plus minus proton. From the angular momentum law, and how about s square plus minus electron is that we already know that from the j square j mj can have the relation j plus 1 h bar square j mj, and also j mj is that mj h bar j mj. Here we already know that from the angular momentum law, and so s square can have the 1/2 and 1/2 plus 1 h bar plus minus electron. So it is that 3 h bar square fourth and plus minus e electron. Like that, isospin square plus minus proton is that 1/2. So it is same. So it is 3 h bar square fourth and plus minus proton. So, and we should think that electron and proton spin state. So electron spin state and proton spin state can have the 1/2 and 1/2. Here it means that, and the spin state is ms 1/2. Then how about the proton? Proton case, isospin is 1/2 and the mi is minus 1/2. It means that there is a I and a mi. Then you can write down, because s and I equal to 1/2, so you can write down and 1/2 and minus 1/2. It means that here is the ms and mi. Then let's denote that it is a plus and minus. It means that it is electron spin and proton spin antiparallel. Therefore, and there are possible states. Possible state is that spin electron and proton spin up state and up down state and down up state and down state. So there are fourfold degenerated. Here it means that fourfold degenerated. So let me think that as an example, and for SG applied to the up and down spin state, then here SG applied to the electron spin up, and here minus proton, then 1/2 spin up and spin down for proton. So it write down 1/2 and up plus minus. And because we already know that here it is an example, so SG applied to the MS and MI, then it is MS H bar, MS MI. So and the SG applied to the electronic spin, but the isospin isospin apply to the MI. So here is the MI H bar, MS MI. So here MS is that plus minus 1/2, and the MI is that plus minus 1/2. Then there are matrices between the SG and IG, because and when you think that here the spin state, the MS and MI state, and that there are possible fourfold degenerated, and the up state, up down state, and the down up state, and down state. Here like that, it is up state, and up down state, down up state, and down state. Here it is the SG case. When you apply this from the diagonalization, and the only diagonalized term have the SG apply to here. When we SG apply SG, here SG apply to this, and it is complete, and it is complete. But other things from the diagonalization and the off diagonal state always equal to 0. So here only diagonalized term survives. It is 1/2 H bar. It is 1/2 H bar. But here in this case SG applied to the spin down case, so it is minus H bar, and the other terms are all of the other terms is 0. It is SG case. Likewise, and for isospin case also, here IG apply to the MS and MI. Then for spin up down, and down up, and down state, and also up down, up, and down, like this. Only this I apply to the nuclear spin state, so it is H bar half. Here apply the minus H bar half. It is H bar half, and it is minus H bar half. The other terms is 0. So and the apply plus h bar have and minus and plus and minus apply, and also the off diagonal term is 0. So then we should think that hyperfine Hamiltonian contains the s dot I, so we should state that the s dot I. In the s dot I case, is the sx ix plus sy iy plus sg and ig. Then we already defined that the ladder operator in the spin s plus is that the sx plus I sy, and the s minus is that sx minus I sy. So from this, and we can know that sx is that 1/2 sx plus s minus, and sy is that 1/2i, and s plus minus, here is plus s minus. So likewise, so here it is that sx and ix, here 1/4 s plus s minus, and I plus I minus is then iy sy and iy is that minus 1/4 s plus minus s minus I plus minus iy I minus. And also the third term, it is simply sg plus ig. So and when you calculate this, and 1/4 and s plus I plus s plus I minus plus s minus I plus s minus I minus, and this second term minus s plus here plus s I plus plus s plus I minus plus s minus I plus minus s minus I minus, and plus sg, not plus but sgig. Then when you see this s here, this term cancel with each other, and also s minus also cancel with each other. So it remained plus minus and minus plus and minus plus. So we can write down as the 1/2 and s plus I minus plus s minus I plus sgig. Then we should think that, and when you apply the s plus is a raising operator, and plus here it is ms and mi. Then because and it raises the spin of the electron, then it is already spin up, and there are only possibilities spin up and down. So and the raising operator of the spin up, there is no possibility, so it is a 0. Likewise, and the I minus apply to the plus minus equal to 0, because and here I minus lowering spin of the downspin, because downspin, lowering of downspin also equal to 0. Then from the angular momentum law, and we already know that the j plus minus j mj, it is that h bar and the square root and the j plus 1 minus mj plus minus 1 and j and mj plus minus 1, and it increase or decrease only the magnetic angular momentum case. So also then when you apply the plus and minus plus, because in this case it is not zero, because that the spin is down state, it makes that the spin up, it makes the spin up state. So and here it makes that the h bar square root and the s plus 1 minus ms plus 1, because it raises operator, and plus plus. Then it makes that h bar square root 1/2 and 3/2 minus it is spin down minus 1/2 and plus 1, and so 1/2. So plus plus. So it makes that h bar square root 3/4 plus 1/4 plus plus. So it is h bar plus spin up. Likewise, and the isospin apply to the plus minus, can have the h bar square root I plus 1, because in this case also I plus generate increasing the operator I minus, so minus mi plus 1 and plus plus. Then h bar square root 1/2 3/2 minus, here minus 1/2 and 1/2 and plus plus. Then it makes that h bar plus plus. How about the s minus? S minus operate to the plus plus case. It is that the h bar square root s plus 1 minus ms minus 1 and also minus plus. Then it is h bar square root 1/2 3/2 minus, because it is a spin up 1/2 and minus 1/2, and it is a minus plus. So it is also h bar minus plus. Likewise, I minus apply to the minus plus. Then it is likewise the h minus, and then it decrease the operator, lowering operator, makes that the down spin state. So now we should calculate the s dot I. If the s dot I apply to the spin up and up, then because it is s dot I is estimated, is defined by this relation. So, and we should copy this. Copy this, and also it apply it apply to spin up state. Then here this I minus apply to this one, it breaks in S plus applied to this, and it makes that 0, and also I plus applied to the plus, it makes the 0. So from the above relation, only here, then here if we apply this I minus apply this, and also S minus apply this, then we can write down as the h bar square and plus plus. Okay, it is not related. Also SGIG okay, so then S dot I apply to minus minus, then it is that and this term apply to minus minus. Here also I minus apply to here, and S minus apply to here, then it makes a 0. So only the half square and minus state is remained. And so let's think that S dot I plus minus and plus minus, then here here S plus apply to here, it makes a 0, and also here S minus apply to here, then it makes that it makes minus, and I plus makes that plus. So here S minus becomes lowering operator, and S plus makes that the plus, so it makes that minus plus. So here you can write down 1/2 h bar square minus plus and plus 1/8 minus plus minus. Okay, so it is h bar square and 2 minus plus minus plus minus. It makes like this. And S dot I apply to minus plus, apply to minus plus, then S minus apply to here, it makes a 0, and when you apply this, S plus becomes minus, I minus becomes minus, plus and minus. So it is 1/2 h bar square plus minus, and also plus minus 1/2 h bar minus plus. So it makes that 2 plus minus 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 plus. Okay, so let's summarize this operator, and also here operator between s dot I something plus minus, well, okay, then plus plus, plus minus, minus plus, minus minus, and plus plus, plus minus, minus plus, minus minus. Then here from this, and the plus plus makes that here like this, quarter h bar square, and also plus minus, plus minus, plus minus, like here. Then we apply the plus minus, then the plus minus, it makes that it is diagonalized relation. It is 0 and only minus h bar quarter, h bar square quarter, and also here minus plus case apply to the minus plus, it is half h bar square, so it is half h bar square. And minus plus, when you apply minus plus, and the plus minus apply, and half h bar square. And also when you apply the minus plus, minus quarter h bar square. So other things and are 0 because of the orthogonality. And also minus minus case is that h bar square. So it can be made that the matrix elements like quarter h bar square, and also 1 0 0 0, and 0 minus 1 2 0 0 2 minus 1 0, and 0 0 0 1. It is not diagonalized, but we should note that here we should diagonalize this term. So, and when we make that this, and it makes the diagonalization. So, and when you think that Hamiltonian, hyperfine Hamiltonian is like this, so we already calculated for s dot I a matrix. So the hyperfine Hamiltonian perturbation Hamiltonian is that hyperfine perturbation Hamiltonian is that a to the 4, the 1 0 0 0 0 minus 1 2 0 0 2 minus 1 0 0 0 0 1. It is here it degenerated. It is kind of degenerated Hamiltonian. It is degenerated Hamiltonian. In previous lecture, we already know that this degenerated Hamiltonian should be diagonalized in degenerated subspace. So, and let's make that degenerate problem here minus lambda. It is a subspace. Let's think that this degenerated subspace, and it should be diagonalized minus lambda, and determinant. Then it is here a plus lambda square minus square should be 0. So it means that plus lambda equal to plus minus half a. So The first lambda is that minus a quarter plus half a is that half a. The other one is that minus half a is that minus 3/4 a. So in the case of for lambda equal to quarter a, in this case matrix subspace matrix is that a over 2 minus a over 2 and C1 C2 equal to 0. It means that C1 equal to C2. Here in this energy, second energy is that quarter A. So E3 state makes that one. Here it is state. This state corresponds to the plus minus, and this state corresponds to the minus plus. It is a linear combination. So, and also plus minus and minus plus linear combination. So in second case, I'm sorry, it is E2 plus. Yeah. It is a linear combination. It is the same sign. And anyway, in second case is that the lambda equal to 3/4 a case. From the matrix, it is a half, C1 C2 equal to 0. Then the C1 equal to minus C2. So in this case, energy state is minus 3/4 a. So E3 state can be write down square root 2 and the plus minus and minus plus. So we can see that the E1 state is from the Hamiltonian. The Hamiltonian is that the a quarter. So, and also E1 state is a spin up of state, and the E2 and E3 already calculated, and the E2 state and E3 state here, and the E4 state is a quarter, and the E4 state is minus state. So, and the in 1s orbitals in the from the hydrogen atom 1s orbitals there is an energy level, but here when you think that the magnetic spin interaction between the magnetic ion, whether nucleus and the electron, there are energy degeneracy like that. The other one is that the E3 state. E3 state has the energy level deep inside 3/4 a, and also here in the E2 state and the E1 state and the E4 state are degenerated, and the energy level state it is a quarter. So it is there is the hyperfine interaction energy, hyperfine energy scale A is that 2 mu 0 over 3 GE mu B GP mu N and psi 1s orbital at 0 square. So we already know that this one, and from the calculation it is isotropic like pi a0 square here cube. Here is a0 is the Bohr radius. So the hyperfine interaction energy can be calculated like that. it is over 5.88 times 10 to the minus 6 electron volt. So there is a very fine energy degeneracy, energy splitting between the E3 state and the other three states. So, and this energy state can be splitted, and also we call it is what this line, and this line splitting is coming from the hyperfine interactions.